Hi, this is 2.5 Pre-Calc Binomial Probabilities, Distributions, and Expected Values. I'm going to make 3 videos out of this. The first one would be the binomial probability. So intro, in my family I have 5 siblings. We want to see how this goes. And I shouldn't say I have 5 siblings, there's 5 kids total. I would like to know how many different ways we can represent the 5 siblings and ultimately find the probability of having 3 girls and 2 boys, which is my situation. Let's write out all the ways that the siblings can occur. So what we do is we take that, there's 5 situations. I could go boy, 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 all in a row. And then I could have 1 girl, I could have 2 girls, I could have 3 girls, and I write out all the possibilities of all these situations. Now if you notice, how does this turn out? 1, 5, 10, 10, 5, 1. So once again, this is Pascal's triangle. So all the different ways that I can write these things out are down here. So if I ask what's the probability of having 3 girls and 2 boys, that would be all of these situations here. So that would be 10 out of my total, which is 32. Now another way to look at this is that I can go ahead and do the binomial expansion on b plus g to the 5th power. That means that I have 5 B, and there's only one situation where that occurs. Then I have 4 B's, 1 girl. That would be 5 situations, which would be right here, and so on. So if you look at these different situations, this does the counting for me. So that simplifies this a lot. So if I want to look at another way to do this probability, I could have done this expansion, taken this 10, and divided by 32. Now there is another way to look at this too, is that I could take the 5 choose 3, which generates this 10 right here. And then I can take the probability of what it is to be a girl or having a girl, that would be 1/2. And then a boy would be 1/2. Notice I take the girls up to the power of 3. That would be meaning having 3 girls. So if I look here, this would be a probability of 1/2 for this boy, 1/2 for this girl, 1/2 for this boy, 1/2 for this girl, 1/2 for this girl. I'd multiply all those together. Since it's 1/2 all the way through, that's not so interesting. But wait, we'll get to some more things that will come about. By the way, that's decimalized there. You can write that down. Now, what if the probability is not 1/2? How can we weight the probability for girls to boys? So here's an example that we can do. In Sassland, the birth rate for girls is 0.65. Yes, you can read that word. What is the birth rate for boys? Well, if that's the birth rate for girls, what we can do is we can find out what the birth rate for boys is by just taking 1 minus the birth rate for girls. And remember that the probability sample space, it's either boys or girls, takes up the whole sample space. So then these two numbers are going to add to 1. So probability of boys is 0.35. Another way to look at this is the probability of not being a boy is 0.35 as well. So what we want to do is try to figure out what's the probability that 3 of them will be girls. Well, what we have to do really is we have to weight the probability for girls higher than 1/2. So we're going to use this same exact formula. I still will have all these different outcomes for the boys and girls. So I'll still have 5 choose 3. But then now this probability for the girls is 0.65. This one for the boys is 0.35. So what we end up with then is exactly the same thing. However, those probabilities have changed, just like I said. Now you can type this into your calculator and make sure you can get this value out. I write them out to 4 decimal places because we usually round to 3, but it's just easier to write out 4. Now this leads to the binomial probability and the binomial probability formula. And so if we want the probability of getting exactly X successes in N trials, with the probability of success on a single trial being P, this is how we do this. Now ignore these 2 boxes. I had to do that for the subscripts. But it would be the choose notation from Pascal's triangle. This P would be your probability of success. Your probability of failure would be 1 minus P. And so what we do call 1 minus P a lot of times is we do call it Q. So you can just go ahead and call it Q. One interesting thing, and maybe it's interesting or not, but sometimes your probability of success is getting an illness. we don't consider that a success, but in a probability model, if that's what we're focusing in on the people who are getting the disease, then that might be our p-value rather than the q-value. So the conditions of a probability binomial experiment. First of all, you need a fixed number of trials. You can't change. Each trial is independent of the others. So if you do replacement, that would be a situation where things are probably independent. If you don't replace items, so for instance, if you're drawing cards, each time you draw a card, that changes the probability of the items left in the deck. So you got to be careful with that. And then there are only two outcomes. It could be rolling a 6, not rolling a 6. That would be two outcomes for some dice. And then also the probability of each outcome remains constant from trial to trial. It does not change. That's another thing with the replacement. If you do no replacement, the outcomes, the probability of the outcomes changes every time you draw something out and you don't put it back. So examples of binomial experiments. Tossing a coin 20 times to see how many tails occur. Two outcomes, heads and tails. The next one, if we look at this one, if we roll a die to see if a 5 appears, well, it's either 5 or not 5. That would be only two cases. Some people think it's 6. No, it's either 5 or not 5. Measuring 20 days to see if it rains or not. The two conditions, rains or not. You might say they're not independent, different things, but whatever. And then watching 20 free throws and either making or missing it. As long as the free throws are independent and they rely on the overall percentage that somebody's usually does, then we're going to go with that as a binomial experiment. Things that are not binomial, rolling a die until a 6 appears. Well, that's because we don't have a fixed number of trials, so that one does not work. Asking 20 people how old they are, not two outcomes. What if I ask, are you 20 years old? Would that be binomial? The answer is yes or no. Yes, that would be. In this case, though, could be many different answers, so that doesn't work. Drawing 5 cards from a deck for a poker hand, done without replacement, so not independent. So let's go to an example and see how this works. What is the probability of rolling exactly 2 5s in 7 rolls of a die? There are 5 things you need to know. First of all, define the success. Oh, I missed it there. Okay, so what happens is that the success would be that we're rolling exactly 2 5s. I don't have that written down, but you can get that down. And so then the probability of success would be 1/6. The probability of failure then, what would that be? Well, that would be 5/6. The number of trials, how many times are we doing this? That would be the 7. Then the success, how many successes do we have? Is it 5? No, we're rolling 2 5s. 5 is just an outcome. 2 is how many we're looking at. So this would be x is equal to 2. So if I put this into my binomial theorem, I have it now on my split screen, but if I do this, I put in n, that would be my 7. So it's going to be 7 choose 2. Then my probability of success would be 1/6 raised to what power? Well, I'm looking for 2 successes, so that's what that has to be. The success is raised to the power of the successes that you're looking at. So in this case, it would be 2. Then the probability of Q would be 5/6, and you're going to raise that to the complement of that number, so it would be 5. So if we look at our answer here, 7 choose 2. Probability of success, I had that wrong, I just changed that. Probability of success is 1/6 raised to the 2. So these two numbers match up, and then I get 5/6 raised to the 5th power. That would be the probability of failure and how many times we have a failure. Here, the failure is not rolling a 5. And if we multiply that out, I believe I got that number right. And so that would be how you find the binomial probability of this situation here. Now let's do another one. Very similar. If I have a spinner and I spin around and I want to land on green. If I want to land on green, what's the probability of landing on green? Well, I hope that you understand that that would be 1/3 because each one of these segments are congruent. So I want to know what's the probability of spinning 4 times, and 3 of those times I want the spinner to come up green. So we got to go through this and define our steps. So the success is landing on green exactly 3 out of 4 spins. Then the probability of success would be 1 out of 3. And then the probability of failure would be, yes, 2 out of 3. And then the number of trials. How many times are we doing this? That would be 4 times. And then the number of successes that we're looking for. And so that would be the 3 times. And so now if we put this all together, let's see if I could do this right, using the binomial theorem, this side's easier to look at, I think. We get 4, that's the number of trials, 3 is the number of successes, 1/3 to the 3, and then 2/3 to the 1, and we get this value right here. All right, so that's how you set up binomial probabilities. You use this formula right here. P is the probability of success, Q is the probability of failure, X is how many successes you have, N minus X is how many failures you have, and then we can do that, N is the number of trials. All right, I will continue on with binomial probability distribution in the next video. Thanks for this one. Take care. Bye.